Hello. In this video, I'm going to go over section 11.4, tangent planes and linear approximations. We learned everything about tangent lines in Calculus 1, and now we're just going to extend it. In case you don't remember, let me remind you what this is, right? So I have a curve, and in this case, it's just happened to be f of x equal to x squared minus 1. If I want to find the slope of the line tangent to the curve at any point, it's a polynomial, right? At any point, I just compute the derivative, so I know that the slope of a tangent line, it's equal to the derivative, which is 2x. If I want to find the slope of a tangent line at a particular value of x, so let's say at x equals 2, then this will be equal to the derivative evaluated at 2, which is 4 in this case. That means that the slope of this line is equal to 4. So imagine if this curve represents position, then the velocity will be equal to 4 miles per hour, whatever units I have. But then another application of this is if I find the equation of the tangent line, then I can use it to approximate my curve at a value very like near 2 in this case. So what I mean is, given the information I have, then I know that the equation of the tangent line is just equal to y minus y1, which is 3 in this case. It's equal to the slope, which is 4 times x minus the x value, which is 2. And I get that y is equal to 3 plus 4x minus 8. And I simplify this and I get that y is equal to 4x minus 5. Okay. So that means that if I'm looking for the value of, let's say I want to know, if I want to know what 2.01 squared minus 1 is, that is super close to 2. I'm here, 2.01. So instead of plugging this into my quadratic function, I can just go find the value and uh, approximate the value with the line, okay? So what I'm saying is that this is approximately equal to, well, I take my equation of the tangent line, so this will be approximately equal to 4 times 2.01 minus 5, okay? So let me actually define this. So what I'm saying is that the equation of the tangent line and the linearization or the linear approximation of f at a are exactly the same thing. So this is equal to, and I just have here that this is f of a plus f prime of a times x minus a, right? Now, if you think about it, and this is now from Calc 2, this is just a Taylor polynomial of degree 1, a line, right? But we saw in Calculus 2 that you can also approximate this with higher order Taylor polynomials. So this will be plus f double prime of a times x minus a squared divided by 2 factorial plus f triple prime of a, x minus a cubed divided by 3 factorial. Now I will be approximating my curve with a polynomial degree 3, which in this case doesn't make sense, but you know what I mean, plus dot dot dot. Now, don't you worry about a thing. We're going to focus on linearizations, okay? But I just wanted to remind you of the possibility of approximating with higher order polynomials. Then that means that if I want to approximate my function at b, I just replace x with b. So this can be approximated by the linearization at b, and this will be equal to f of a plus f prime of a, and here we go, b minus a, okay? Okay, perfect. So we're going to do the same thing now, but in higher dimensions. So now, instead of a tangent line, we're going to have a tangent plane, and the linearization will be approximating the surface with a plane, okay? So I'm literally going one dimension higher every single time, okay? So let's see, this is what's happening. In this case, I'm just giving you z equals f of xy equal to x squared plus y squared. And now it's no longer a one-dimensional problem. Now my domain is two-dimensional. So what we do is we fix a value of x and we look at how this changes in the direction of y. So by that I mean, imagine here, this is what I'm focusing on now. This is the y-axis. This is the z-axis, right? So if I fix a value of x, it's just I'm looking at this curve. So if I fix a value of x, I'm looking at this curve. I believe this is the point 215. So I'm fixing this at x equals 2, and I'm fixing this as x equals 2, but then y changes, right? So I can parameterize that. And then if I compute the slope of the line tangent to the curve in the direction of y, right? In the direction of y, the slope of this line will be given by the slope of the line. It's equal to the partial derivative in the direction of y evaluated to 1, okay? Same way, I can just fix a value of y now and just focus on how my function changes, but in the direction of x. So if I do this, I will be looking at this curve. I'll be looking at this curve, and then this would be the line tangent to the curve at the point 215. So then again, the slope of this line will be f of x evaluated at 1, okay? So we're going to be looking at the plane that we construct by taking the two tangent lines. So then this is the equation that we want. We want to find the plane that contains both of those tangent lines. And I'll show you what it looks like after I define a couple of more things, okay? So now instead of the equation of the tangent line to the curve, now it's no longer a curve, now it's a surface, and it's no longer a line, now we have a plane. So we're looking for, we want the equation of the plane tangent to the surface at a given point, and this plane contains both of the tangent lines. Now you're wondering, why are we doing this? Well, same reasons we did it in calculus 1, maybe to approximate the function near a point. So it's easier to plug in into a plane than into a complicated surface. And then obviously the same idea, right, to approximate a complicated surface using a plane. And something that we didn't use it for in calculus 1, but now we'll use it for, is to define differentiability in higher dimensions, because it is a little harder than in one dimension, okay? All right, so let me formally define this. Tangent planes. So if S is a surface with equation f of xy, and I need my partial derivatives to be continuous, and I'll show you why in a minute, then P, defined with x naught, y naught, z naught, it's a point on S. On top of that, I have that C1 and C2 are the curves obtained by intersecting the vertical planes, where y naught and x naught. So by that I mean here, this is these two curves. The intersection of these two curves is the point 215, right? That's how I computed it. So this will be the intersection of those planes, the plane x equals 2, y equals 1. And then what else? And then I also know that we also have that T1, T2, that's what I'm calling the two tangent lines, the line tangent to both of those curves at the point. Then the tangent plane to the surface is defined by the plane that contains both tangent lines. Okay, so one more time. Here I don't know if you can see the curves here. Those are the two curves, C1, C2. These are the two tangent lines, okay? And this is the plane that is spanned or formed or created by the two lines. So it contains both of them. Now you can see here a different point of view, different POV, if you will. Now, since I'm recording, GoodNotes does not allow me to click on this to show you, but do click in this and it'll take you to this graphs, and you can play around with it and maybe like move it around so that you see what being tangent means, which hopefully you understand. It means exactly what it meant in calculus 1, right? It'll be the plane touching that curve at that point, and it contains the two tangent lines. Okay. Now, how do we find the formula for this tangent plane? So let's see. Suppose f has continuous partial derivatives, an equation of the tangent plane to the surface z equals f of xy at the point x naught, y naught, z naught is, so I'm not going to just give you the formula. I'm going to get to the formula with you. Okay, so first of all, you know that the equation of a plane containing x naught, y naught, z naught, and having a normal vector a, b, c It's given by a x minus x naught plus b y minus y naught plus c z minus z naught equal to 0. Now, finding this vector that it's normal to the plane, it's not trivial. So instead, I'm just going to use algebra and the understanding of partial derivatives to find the coefficients a, b, and c. First thing I'm going to do is I'm going to divide everything by c. So that takes me down one variable. So if I divide everything by c, assuming z is not equal to 0, obviously, then I get that a times x minus x naught divided by c plus b divided by c y minus y naught plus z minus z naught, it's equal to 0. Okay. Now from here, what do we get? From here we get that z, it's equal to z naught. And then I will conveniently call this two things. I'm going to call a over c, I'm going to call it negative a, and b over c, I'm going to call it negative b, so that when I move into the other side, I get rid of, I don't have any negatives. My formula does not have any negatives. So I have z here, I move z naught to the other side. I'm about to move a times x minus x naught to the other side. So I get that this is plus a times x minus x naught plus b times y minus y naught. And we need to find a and b. So this will be the equation of my tangent plane once I find the values of a and b. So let's see what they are. Let's say here we need a and b. So what I'm going to do is, let's say I fix y equals y naught. If I do that, then this whole term goes away and I'm left with z equals z naught plus a times x minus x naught. Now, when I'm fixing y equals y naught, then that means that this is the equation of the line tangent to the curve, right, at the fixed value of y in the direction of x. Therefore, a must be equal to the partial in the direction of x evaluated at the point. So from here, I get that a must be equal to the partial with respect to x, or in the direction of x, evaluated at the point. Same way, I can just now I can fix y equals y naught. If I do that, then this goes away, and I'm left with z equals z naught plus b times y minus y naught. And then this is again the equation of the line tangent to the curve in the direction of y. So from here I get that b must be equal to the partial in the direction of y evaluated at the point. So if I combine these two things, right, if I combine all this information, let me make it smaller. So resize, make it a little bit smaller. If I combine these two, I get that then the equation of the tangent plane, it's given by z minus, or z equal to z naught plus partial in the direction of x, evaluated at the point, x minus x naught, and then I do partial in the direction of y, evaluated at the point, so plus fy, evaluated at the point, and then y minus y naught, okay? Now, keep in mind that these two things, this partial in the direction of x, you have to evaluate it at the point, and the partial in the direction of y, you have to evaluate at the point. So these are numbers, just like in Calculus 1, right? These are numbers. Okay, let's do an example. Find an equation of the tangent plane to the surface, z equals the natural log of x minus 2y at the point 3, 1, 0. Okay, so let's see. This is going to be your f of xy, and this is the point x naught, y naught, z naught. So this is x naught, y naught, z naught. Okay, so this, we have everything that we need to do this. Okay, so first of all, we know that z naught, it's equal to the function evaluated at x naught, y naught. So this is equal to the natural log, or let me just do one intermediate step, f of 3, 1, which is equal to the natural log of 3 minus, and then 2 times 1. So it's 3 times 2 times 1, which is 2. So you get the natural log of 1, you get 0. So all this work just to get that z naught is equal to 0. What else do we have? Then we know that we need to find the partial respect to x. So fx is equal to, I know you know this, but let me maybe recall here, recall. If you're taking the derivative with respect to x of the natural log of x, or natural log of a function, this is going to be equal to 1 over the function times the derivative of the function. Now that we're doing partial derivatives, it'll be exactly the same thing. So this is going to be equal to 1 over the function. Let me go back to blue. This is going to be 1 over the function, so x minus 2y, times the derivative of the function with respect to x, okay? So this is going to be times the derivative of the function, but I'm going to do this with respect to x, okay? So this is going to be equal to, well, that times 1, okay? And now I have to evaluate this at the point 3, 1. So I get that this is equal to, 1 over 3 minus 2 times 1. You get 1 divided by 1, you get 1. And then we need fy. Well, fy, it's equal to, I do the same thing, I get 1 over x minus 2y times the derivative of x minus 2y with respect to y. So I get negative 2. So this is equal to negative 2 divided by x minus 2y. That tells me that my partial respect to y evaluated at 3, 1, it's equal to, well, negative 2 divided by 3 minus 2 times 1, which is negative 2 divided by 1. We get negative 2. Okay? That's it. That's all we need to find the equation of the tangent plane. So then that tells me that equation of tangent plane, right? Plane tangent to z equals to the natural log of x minus 2y at the point 3, 1, 0. To make this smaller so that you see the formula again. It's going to be equal to, let me see, z. So here we have z. And then z naught, well, z naught it's equal to 0. So 0 plus partial with respect to x evaluated at x naught, y naught. So this would be this, right? It's 1. So I get 1 times x minus x naught, but x naught is equal to 3. So that's that. And then I do the same thing for y. So now I have partial respect to y, or in the direction of y. So I get that this is negative 2. So this is this negative 2 and this negative 2. And then I get y minus y naught, but y naught is equal to 1. I'm going to simplify this, and this is going to be equal to, so from here I get z, it's equal to x minus 3 minus 2 times y minus 1. So z, it's equal to x minus 3 minus 2y plus 2. Z, it's equal to, and I'd like to have like the order have x, y's, and then constant. So this is going to be equal to x minus 2y minus 1, okay? That's it. That is the equation of the plane tangent to the surface, natural log of x minus 2y at the point 3, 1, 0, okay? Perfection. Now, the beauty of this is that when x, y is near to 3, 1, then this tangent plane is a good approximation of the function. Okay, so one more time, if I'm near 3, 1, I can use my tangent plane to approximate the function. Okay, perfect. So let me just make sure that we know this. So I'm saying f of x, y can be approximated by x minus 2y minus 1. That's exactly what I'm saying. Okay, so i.e. f of x, y can be approximated by x minus 2y minus 1. Okay, perfection. Now, here's the question. In calculus 1, we have that it is enough for the derivative to exist. Like if you find the derivative and you get a number, then you're done, right? So in calc 1, let me remind you, in calc 1, if I have a graph here and then I have my function f, and this is a, and then I can actually go here and I can find the slope of a tangent line, this is enough for the derivative to exist. Then we say, well, if f prime exists, then f is differentiable at a. Okay, now in Calc 3, we need the partial derivatives to exist, but we also need them to be continuous. So what I'm going to do is I'm going to look at what happens if they're not continuous. Okay, so let's see. So even though we have proved that this function is continuous, right? The limit as xy goes to 0, 0 of this function, we've proved that it's equal to 0. And by defining f of 0, 0 as 0, we're removing the discontinuity here in the denominator, okay? Now, you can show that even though the function is continuous, you can show that the limit as xy goes to 0, 0 of f of x, xy, this is not equal to the partial respect to x evaluated at 0, 0. Same thing happens for the partial, same happens for the partial in the direction of y, okay? So that means that this function, the partial are not continuous. So partials are not continuous, okay? Now, if they're no continuous, I'm going to show you what happens in this case, knowing that the partials are not continuous. Then what happens is that we're going to get a bad approximation. So let me show you what I mean. Okay, so let's see. So let's find, under these circumstances, let's find the equation of the tangent plane, okay? Now what do we need? We need z naught, which is equal to f of 0, 0, which according to this is just equal to 0. Then we also need the partial respect to x evaluated at 0, 0, which in this case, it's a lot easier to just use the definition rather than using the quotient rule and doing all of this and that. So I'm just going to do that. So this is going to be the limit as h goes to 0 of my function. So I'm doing in the direction of x, so I do 0 plus h, and then 0 minus f of 0, 0 divided by h. This is the limit as h goes to 0. So if I go here when x is equal to h and y is equal to 0, right? So x is equal to h and y is equal to 0, I get that this is equal to, what is this equal to? This is equal to h squared times 0 divided by h squared. So this is just 0. And then we say divided by h squared minus 0 divided by h. So this is equal to 0. Okay? You do the same thing, but in the direction of y, and you get that this is the limit as h goes to 0. But now I'm moving in the direction of y, so I fixed x. I have to fix x. So this is 0, 0 plus h minus f of 0, 0 divided by h. And again, you get that this is 0. When I combine these two things, I get now that then the equation of the plane, which is given by z equal to z naught plus fx 0, 0 times x minus 0 plus fy 0, 0 times y minus 0, right? I'm replacing x naught and y naught with 0, 0. And then z naught is also 0. So you get that the equation of the tangent plane, it's equal to, well, this is 0, and this is 0, and this is 0. So you get z equal to 0. So what this is saying is that I can approximate my surface at 0, 0 with the plane z equals 0. So this is just here on the xy axis. So this is what we're saying. And this is obvious just by looking at this, right? This is obviously not a good approximation. So let me try to right? This is below my z equals 0 plane, okay? So this is below the z equals 0 plane, and then I have this. Let me just finish this real quick, right? So it'll look something like this. And this is obviously not a good approximation, okay? So this is what I was saying, that we're going to be able to use the tangent plane as our definition for differentiability, okay? So we were able to find the partial derivatives. We were able to find the partial derivative in the direction of x is equal to 0. Same with the partial in the direction of y. We were able to write an equation for the tangent plane, but obviously just by looking at this, it's not a good approximation. And the reason why it's not a good approximation is, well, if you try to get to that point and draw the tangents, you're not going to get a continuity. They're not the same from all sides, okay? So we say that the function is not differentiable. So since z equals 0, it's not a good approximation for z equals f of x y at 0, 0, then z is not differentiable at 0, 0. Okay, perfect. Now let me give you the actual definition of differentiability. So I'm going to let you look at this for a second. So it has a lot of symbols. So this says if z is equal to f of x, y, then f is differentiable at ab if delta z, which means the change in z, can be expressed as delta z equal to partial and then a change in x and then partial respect to y and then delta y and then some epsilons, where both of the epsilons go to 0 as the change in x and y go to 0. What does this mean? Okay, it's a lot of words. So what it actually means is, well, we know that delta means change. So what this is saying is that the change in z, so z minus z naught, it's equal to fx ab and then x minus x naught plus fy ab y minus y naught plus some error. That's what it says, okay? And I need that error to be super small. So this is some error. This is super small. It has to go to 0. It must go to 0 for this to be a good approximation. So what this is saying is, hey, if my partial derivatives exist near AB, and we saw that they must be continuous, it's not enough to exist. If they're also continuous, then f is differentiable at AB. And that will happen if and only if you can approximate your function with a plane, okay? That is it. So all this wording is just to say if, if we can find a tangent plane that is a good approximation. Okay? And then again, that happens if the partial derivatives are continuous. Okay? To the function, to f of x, y at AB. Okay? It's all the same. Let's see. Is f of x, y equal to y plus sine x over y differentiable at 0, 3? Well, let's see. What do we need to show? So we need to show, in order for it to be differentiable, the partials have to be continuous, okay? Not only defined, they also have to be continuous. All right, so let's see. So I'm going to find them. So fx of xy, it's equal to, I'm going to take the derivative with respect to x. So the derivative of y will be 0, and then I have to use the chain rule. So this is going to be equal to cosine of x divided by y times the derivative of x divided by y with respect to x. I get 1 over y. That tells me that f of partial 0, 3, it's equal to cosine of, and then when x equal to 0, I get 0 divided by 3, and then 1 divided by 3. So this is equal to cosine of 0, which is 1 times 1 over 3. It's 1 over 3. Now I take the partial respect to y, and I get that this is equal to 1 plus, actually minus, and then this would be cosine of x divided by y, and then this is the same as saying x times y to the negative 1. When I take the derivative with respect to y, I get negative x y to the negative 2. So this is the same as 1 minus cosine of x divided by y times negative x divided by y squared. That tells me that f partial 0, 3, it's equal to, well, I plug in x equals 0, y equals 3, and I get that this is 1 minus, and then cosine of still 0, so I get cosine of 0, which is 1 times, oh, all this work just to get 0. So this is equal to 1, okay? And then you say, well, if I were to find the limit as x, y, so I have here my derivatives, I get that. And the beauty of this is that this is very easy to see that they're continuous, because you know that the limit as xy goes to 0, 3 of fx xy, it's equal to the limit as xy of, uh, of what is this? Cosine of x divided by y, 1 over y. This goes to 0, 3. It's equal to, you plug in, you get a number, you're done. You get 1 over 3, which is the same as fx 0, 3, right? So this is continuous. And same thing happens if you do it for the partial with respect to y. This goes to 0, 3, and then fy, xy. So as a rule of thumb, like if you have one and only one definition, if we're not talking about a piecewise defined function, this is pretty straightforward, right? So this is going to be, what is the derivative? You get 1 minus cosine of x divided by y minus x divided by y squared, which is equal to 1, which is the partial, evaluated at 0, 3. So that means that f is differentiable at 0, 3, okay? Perfection. Let's see, what else do we have? Now, if it's differentiable, then the linear approximation is reasonable, okay? And it is differentiable if the partials are continuous. Now, we've been doing this already, but long story short, let's define the linear approximation, okay? So, one more time, the linear approximation or linearization of f at x naught, y naught is, of course, we need to find, this has to be differentiable, right? So if f is differentiable, meaning the partial derivatives are continuous at x naught, y naught, then I get the linearization is Lxy, it's equal to, this is just the equation of the tangent plane, right? And then I take the partial x naught, y naught, and then we have x minus x naught plus the partial respect to y, and then x naught, y naught times y minus y naught. I don't know if you noticed this, but this is just the equation of the tangent plane. Same like in calculus 1, right? The linearization and the equation of the tangent line are the same thing. Now in calc 3, the linearization and the equation of the tangent plane are the same. So this is just, I'm gonna say, this is just the equation of the tangent plane, okay? Tangent plane. All right, perfect. So it says find the linearization of the function that we dealt with before and use it to approximate this. Okay, so I'm going to take this with me. What do we have? Here we have both of our functions, so let me take this with me. So copy, paste, and then we see that we know that the linearization by that we just defined that. Okay, so by definition, the linearization Lxy, it's equal to, let me make it smaller so we can actually find it. It'll be the function evaluated at x naught, y naught. So I need to find here the function f evaluated at 0, 3. It's equal to y is 3 plus sine of 0 divided by 3. So this is equal to 3 plus 0, so just 3. So I get that this is equal to, the linearization will be equal to f of 0, 3, which is 3. So I get 3 plus, now I get the partial. So this is 3 plus partial respect to x. So I get 1/3, and then I get times x minus x naught, which is 0. And then the partial respect to y, I get 1, y minus, and then I get 3. So I get that this is equal to 3 plus 1/3 x plus y minus 3. So all this work to get that this is 1/3 x plus y, okay? So that means that near 0, 3, this should be a good approximation, right? This is the equation of the tangent plane, and I can use it to approximate the function near that point. So in particular, that means that f of 0.13.1 can be approximated by the linearization of the function at 0, 3. So by just plugging in x equals 0.1, y equals 3.1. So this is equal to 1/3 times 0.1 plus and then I get y it's equal to 3.1. So this is approximately equal to, what do I get for this? I get that this is approximately equal to 3.1333. Okay, perfect. I have one more example for you. In chemistry, the rate of chemical reaction R often depends on both temperature T and concentration of a reactant, okay? Now, a given operating point, the function RTC can be approximated using linearization. So we don't have a formula for the reaction R, but we can approximate it using linearization. We have two variables, so it's like T is X and C is Y, okay? Now, this is the information we have. T naught, the temperature, the initial temperature is 25 degrees Celsius. The initial concentration is 1 mole per liter. The reaction rate at the initial point is zero point 0.5, and then the reaction changes at a rate. So these are derivatives, right? So the reaction changes at a rate of, and here we have temperature and here we have concentration. So this is going to be the change in the reaction with respect to temperature, and this is going to be the change in the reaction with respect to concentration. Okay, so let me just find what the linearization of the reaction will be. It's going to be equal to, as usual, we take the point, right? The reaction at the initial point, so T naught, C naught plus, then I'm going to take the derivatives, the partial derivatives, evaluate them at the point, and then this would be T minus T naught, and then plus the partial respect to concentration, evaluated at the initial point, and then concentration minus the initial concentration. So given the information we have, this is going to be R of 25, 1 plus, and then the change in the reaction with respect to temperature is 0.02, so 0.02, T minus T naught, well, T naught still 25, plus the change in the reaction with respect to concentration, it's zero point 0.8, and then we have T minus, and then C naught, it's equal to 1, okay? So what this is doing is this is telling me exactly what we can approximate our reaction at any given temperature and concentration. This should be C, temperature and concentration, okay? As long as we're like near 25 on 1, okay, we know that. So we're trying to find, it says estimate the reaction rate when the temperature increases to 27 and the concentration increases to 1.05. So what this is asking me to do is to approximate the reaction when temperature is 27 and concentration is 1.05, okay? So this is approximately equal to, well, R of 25, 1, it's right here, it's 0.5, so I could have just replaced this with 0.5, 0.5. So this is 0.5 plus 0.02, and then the given temperature now is 27 minus 25 plus 0.8, and then 1.05 minus 1. So this is equal to, I get uh, 0.5 plus 0.02 times 2 plus 0.8 times 0.05. You put everything in your calculator and you get that this is 0.58. You need some units. I got moles per liter seconds. Okay, perfection. All right, I hope everything made sense. Bye bye.